I'm Steve Hoover, founder of Redwood EDA, and this screen capture video accompanies the blog post Visual Debug for Formal Verification. So what we're looking at here is a run of the formal checker on the Warp 5 core. This is running a 4-stage version of a RISC-V configuration of Warp 5, and we're running the formal framework from Claire Wolf called Symbiosis, and also Claire's formal checker framework for RISC-V called RISC-V Formal. And we see that we've got a failure uh, from the checker. This is a register checker. So I'm going to open up the counterexample. So the formal tools have produced for us a counterexample trace file, which traditionally you would debug using a waveform viewer. And we can do that in Makerchip here. We've got our waveform. We can drill into the instruction pipeline and get all this detailed simulation data to debug. We're going to do better than that, of course. You read the blog post. We're going to use Visual Debug. So the War5 core uses Visual Debug to create this custom visualization of what's happening in the War5 core. So we can see the instruction being decoded here, the what's happening in the integer register file, the data memory, CSRs, etc. Over here we see what's happening in the RISC-V formal checker. So this is the RISC-V formal interface. We see the instructions being presented to the RISC-V formal, and since this checker is the register checker, we see what's happening with the registers, source and destination registers of each instruction. All right, so let's get our bearings here. We've got many cycles of just reset. I'm going to step through the reset cycles, and here we start executing some instructions. And with this visualization, you can see each instruction being decoded and accessing registers in the register file. And we can step through, and we should, before long, see a failure here. And that'll happen at the end of the simulation. So let's see. Oh, here we go. So cycle 26, we're checking, and we do actually see here in red the visualization has detected a mismatch, kind of doing similar things or reflecting for us what the RISC-V formal framework has detected. So in this case, the RISC-V formal framework is telling us that the shadow model for this particular register is expected to have this value, but we're actually seeing a value of 0 when we execute this instruction and read that register in RS1. So the instruction that's failing is a branch equal instruction. And we can see this 0 value in x21. This is the problem. We can see that it's accessed from the register file. And look, this is orange. So obviously visualization has found something funky with this register. The orange here is indicating that the register is in what's called a pending state. And pending is used by load instructions. So a load is going to go off to memory, and that memory access can take a while. And while we're waiting for that value to come back from memory, we mark the register as pending, and we allow the execution of instructions to continue. So not surprisingly, we're doing something interesting here. Formal has a way of finding interesting cases for us. That's why it's so great. And what should be happening? We should be reading this pending state, and that should result in a replay. We do see here that this branch equal is shown in gray, which is indicating that it's not actually being retired. So something is happening to this branch equal. It is being presented strangely, though, to RISC-V formal for checking. I think, yeah, so I'm looking for this trap indication. So this instruction here, this branch equal is trapping. That's why it's gray most likely. Um, and the way RISC-V formal works, when you have an instruction that traps, um, that's not supposed to commit its results, you need to still convey that to RVFI um, so that it can make sure, recognize that you had a trapping instruction. And so that's what's happening here. We're presenting that trapping instruction. It should not actually be presented to RVFI because it should be replaying, and that should take precedence over the trap. So why do we seem not to be getting that replay? We can check down here. This waterfall diagram is representing to us what's happening to the instructions as they march through the pipeline, various events, hazards, and whatnot. So we're seeing the instructions marching through their pipeline over time. This is the branch equal instruction, and we actually see the RS1 here that is reading X21. The reason it's actually highlighted here is because it's bypassing the register file, or it's being forwarded from this LBU instruction to the branch equal. And so just to quickly explain bypass, actually we have a diagram here. Let me go. So this is depicting the register bypass. So the reason you do register bypass is because in this blue pipeline stage, we're executing the instruction. This is the arithmetic logic unit. It's producing a result. And if you have an instruction immediately following this that needs that's reading that result register, you don't have time to write that into the register file and then read it out. So you have to bypass the register file by forwarding that register value back to the arithmetic logic unit for the next cycle of execution. And here we're not talking about one instruction to the next. We're actually here doing 2 cycles of register bypass. But we're not getting the replay indication that should result in a replay trap that we should see here. What we are seeing, this AT is an aborting trap. And what we're not seeing is this replay. So where do we go from here? I guess we could look back at the code and try to figure out, we've narrowed this down pretty well just from the visualization. Often you'll start with the visualization and get a high level picture, and then, where the visualization sort of gives way, you'll dig into the waveform. I think here we have a pretty good indication that we have this bypassing register value that should be tagged with replay, or should be tagged with pending, that either we're not getting that pending indication or we're getting the pending indication, but we're not triggering the replay based on it. So let's try to find the register bypass logic that should be forwarding that pending indication. So let me search here for bypass, because I know there's some bypass named signals here. And yeah, this is the register logic. So here we are, and this is TL-Verilog code. TL-Verilog is my focus with Redwood EDA. You can use the same methodology with any hardware description language. The visualization, as the blog mentions, is based on traces. Traces are standard. Any simulation environment based on any hardware description language will produce waveforms. So in any case, in this case, this is the logic for each source register, and it looks like this is where we figure out the register value and its pending state. So we should be here reading either from the register file or from bypass. So, okay, here's reading from the register file, value from the register file, and pending is also stored in the register file. And then these would be the bypass cases. So this is where we're comparing the destination register of previous or previous instruction with this register index. And this in TL-Verilog, you can read this as ahead by 1. So this is the destination register of the instruction that's one ahead of us in the pipeline. In other words, the previous instruction. So if the previous instruction's destination register matches registry index matches our registry index. We might need to bypass. I think this is an indication that the destination register is valid. There is something to bypass. And the value that we're going to bypass is the result from the previous instruction. And so the result as well as the pending. Okay, and then so this is the one-stage bypass, and this would be the two-stage bypass. So the result from the 2 stages ago, and here we go. So here's our bug, I think. We've got, we're accessing the pending bit from not 2 cycles ago, but 1 cycle ago. So we've got a cut and paste error here. This is a good lesson in why you should never have cut and paste code. This should really be written inside a loop. But let's fix the bug. So let me jump back to the source. And so the highlighted line here is the line that we were looking at. This is, so as I mentioned, Warp 5 is generated code. So this is the source code that's generating the native TL-Verilog code here. In the source code, we have expressions like this that are used to conditionally generate logic. So in this case, if we have 2 cycles of bypass, then we want to generate the 2-cycle bypass code. And here indeed is our bug. So let's fix it. And that is saved. And we should at this point be good to go.